Okay, class, please turn to page 14 on your notes. We look at this example, 3.21. Find mesh current I1 and I2. So you look at this configuration. It has a direct current source, and it has three resistors, R1, R2, and R3. And it also has a direct voltage source, Vs, equals 6 volts. And please pay attention to this. This terminal is upside down because we usually put a positive terminal of a current source on the top. But this one is the minus terminal is on the top and plus terminal is on the bottom. So because we need to use mesh current analysis. So for mesh current analysis, First, we need to define, First, we need to define mesh current, and we usually define the mesh current as a clockwise direction. So here I already write the mesh current for you, I1 and I2, and then we look at loop 1. So this is loop 1. This is loop 1. So for loop 1, so within loop 1, I1 is flowing clockwisely. And then because there is a current source, so since I1 will be flowing here, I1 will be flowing along this loop. So it means I1 equals Is. So because they are identical. So I1 will be equal to Is, which is 0.5 amp. So we have already got I1. And then we look at loop 2. So within loop 2, and yes, we start from the left bottom of the loop, and there's I2 flowing into loop 2. And because when we're doing KVL, if you remember, we are doing KVL for mesh current analysis, and KVL says the voltage, the summation of a voltage within a loop is 0. So, and because the current I2 flows through a resistor, flows through R2, and a resistor always consumes energy. So the current will flow into the positive terminal of a resistor, and because it consumes energy. Also, I2 also flows through R3, and then so we know because R3 also consumes energy, so we know the I2 comes into the positive terminal and leaves out from the negative terminal of R3. So KVL at loop 2 start from here. So we meet the 8 ohm resistor however, because I1 is in opposite direction of I2. So the voltage consumed by R2 is actually 8 times I2 minus I1. Okay, because this R2 is shared by I2 and I1, and we follows because we look at the loop 2. So we follows the direction of I2, and I1 is in opposite direction of I2. So if the voltage between across the voltage across R2 is 8 times I2 minus I1 and plus, okay, by the way, this is plus. This is plus because it meets the plus terminal first, and then plus 2 times I2. This is the voltage across R3, and then it meets minus terminal of the voltage source first. So it's minus 6 equals 0. Okay, so this equation, the second equation becomes 8I2 minus 8I1 plus 2I2 minus 6 equals 0. And it is 10I2 because I1 is 0.5 M. I1 is 0.5. So 10I2 minus 8 times 0.5 minus 6 equals 0. We have 10I2 equals 10. And then I2 equals 1 amp. So we solve I1 and I2 by using mesh current analysis. 好，这一题呢，这一题它的 R2 8 欧姆的 R2 呢，它是由 I1 跟 I2 共用的，在这里，它是这里啊，我用一个比较显眼的颜色，我用个红色，好，请大家稍等。它因为这个8欧姆的电阻呢是 I1 跟 I2 共用的，所以我们知道这里如果是用 I2 的观点呢，那你 I2 要扣掉 I1。好，那不过我们先来看这个 loop one 好了，左边这个小 loop， 因为 I1 呢 ，I1 是这样流的，那在最左边这个分支呢 ，I1 就等同于 IS。所以呢，所以我们马上就知道 I1， 因为在左边它只有一个 branch， 然后它是由下往上的，所以我们就知道 I1 会等于 IS。然后我们求出 I1 之后呢，我们来看右边这个小 loop。那刚刚说的就是 R2 是被 I1 跟 I2 共用的，然后我们要呢，就是我们的方向是由 I2 的观点。所以是 I2 要扣掉 I1， 而且是加号，因为我们碰到呢电阻永远是耗能，所以电流呢永远是从电阻的正极流进去，所以一开始是一个加号，然后再来看到 I3、R3，那 R3 它这个电阻呢，它只有 I2 流过，所以这个比较单纯，而且呢电阻是耗能，所以 I2，所以我们永远先碰到电阻。电流呢，永远就是流入电阻的正极，所以既然是正极呢，我们就是加 I2， 然后加二倍的 I2， 然后呢，再碰到这个电压源，那电压源呢，我们是先碰到它的负极，所以是-6等于0，那我们就它有两个变数，那我们有两个 loop， 那列出两个方程式。不过这总共有3个 loop， 因为外面最大一环也是一个 loop， 但是我们在做这个 mesh current analysis 的时候呢，都是看最小的 loop， 就是看 loop 1跟 loop 2。Okay, so hopefully you can understand. Okay, and then we look at this second example, Wheatstone Bridge. And Wheatstone Bridge is a circuit and which is commonly used to identify the value of unknown resistor. So identify the value of unknown resistor. So in this configuration, we have a voltage source and we have three known resistors. They are R1 is here, R2, R4, and they are known. But R3 is here. R3 is the resistor that we want to measure its resistance. Okay, so so how can we use R1, R2, and R4? How can we use these three resistors to measure the resistance of R3? Okay, so the way is we can adjust R4. R4 can be adjusted and to maintain zero current flow between A and B. So there's no current flow between A and B. So some people also draw the configuration of Wheatstone bridge as this. So you may always see a Wheatstone bridge like this. So this is R1, this is R2, this is R4, and it can be adjusted. So this arrow means this R4 can be adjusted, and R3 is the unknown resistor and connect to a voltage source. Okay, so some people draw the configuration of Wheatstone bridge as the shape of diamond. Okay, so how can we prove this? So if we make the current between A and B is 0, how can we know the resistance of R3? So we apply mesh current analysis and to show you. So let's apply mesh current analysis. And then the first step is we need to define mesh current. So on this configuration, mesh current are already assigned to you. So we have I1, I2, and I3. So they are flowing clockwise. So there's no problem. So we look at the loop 1. Loop 1 is this big loop on the left. So we look at the loop 1. So we need to apply KVL within loop 1 after we define the mesh current, right? So loop 1, KVL. So start from the bottom left. So start from here. We have minus VS, and then it means R2. So this is positive, negative, but R2 is shared by I1 and I2. So we have plus R2, I1 minus I2. Okay, and then it goes to R4 because it is this direction, right? This direction within loop 1, and then keep going to R4. So we have plus, because the resistor always consumes energy, R4 times I1 minus I3, because I1 and I3, they are in the opposite direction. So, and then the summation of the voltage within a loop is 0. So this is the first equation. And then, okay, and then we look at loop 2. Or we can say mesh 2, right? Loop 2 is here. So we start from this point. We start from this point, and then we meet R2 first, and R2 is a resistor. It always consumes energy, so we have a plus. We must meet the plus terminal first. So plus R2, and then it's I2 minus I1. Because we need to, right now, we need to write the equation from the perspective of I2. Okay, and then we come here, we come to R1. So R1 also consumes energy, so plus R1 times I2 equals 0. Okay, so, and then between A, B, there's no resistors. So we complete the equation because within I2, within this loop 2, only R2 and R1 consume energy. Okay, and then we look at the loop 3, the last loop. So we start from the bottom left, start from here, and we meet R4. So R4 times I3 minus I1, and then so plus R3 times I3 equals 0. Okay, so we complete these 3 equations, and how about let's assign, this is equation 1, this is equation 2. So from equation 1, so we have what? So from equation 1, it becomes R2, I2 minus I1 equals minus R1, I2, right? So it becomes, if we put R2 to the right side, so if we divided both ends divided by R2, so this is I2 minus I1. We put I2 on the left, so this is I2 equals minus R1 divided by R2. So they are the same, right? And then from equation number 2, same thing. It becomes I3 minus I1 divided by I3 equals minus, this is R3 divided by R4. This is R4. Wait, this is R2 over R1. R1, R2. Okay. This is, am I right? I1 minus I2 times R2. Yes, is it correct? Okay, times R1. Okay, and then R2. Okay, it's correct. So let's focus on these 2 equations. If I2 equals I3, what does that mean? If I2 equals I3, what does that mean? If I2 equals I3, that means this one is the I2, this one, they are the same, which means if I2 equals I3, then I2 minus I1 divided by I2 equals I3 minus I1 divided by I3. Okay, so you can imagine that if they are the same, you put, so they would be the same, you use another new variables, and these two equations, they both have A minus I1 divided by A. So they are the same, which means these two are the same, which means minus R1 divided by R2 equals minus R3 divided by R4. And then this equation becomes, so we have R1 times R4 equals, okay, how about I write it on the top? I write it on the top, so it's here. Let's erase this. It becomes R1 times R4 equals R2 times R3. Okay, and so since R1, R4, R2, they are known, only R3 is unknown. So we have this R3 equals R1 times R4 divided by R2. Okay, so we got our proof. So if you remember, if we look at the problem statements, R4 is known and can be adjusted to maintain the zero current flow between A and B. So if I2 and I3, they are the same because they are in the opposite direction, it means zero current flow between A and B. Between A and B. So if there's zero current flow between A and B, we can determine the value of R3 by just use R1 times R4 divided by R2. Okay, so 好，那这个呢，就是我们用我们的 mesh current analysis 去看 loop one， 我们或是说 mesh one、loop two 跟 loop three， 所以我们就是用这个 KVL 在 loop one 里面，那一样，那我们我们就举 loop one 做例子好了。loop one 呢，我们从这个左下角出发，我们碰到一个直流的电压源，那我们先碰到负号。既然先碰到负号呢，所以我们就是负 Vs。那一直走一走，走到 R2 的时候，那 R2 这个电阻永远是耗能，所以我们就是有个正号。那因为呢 ，R2 是由 I1 跟 I2 共用的，那因为我们只是在 loop one， 所以我们要遵循 R2 的 R1 的方向，那所以是 R1 减 我们先遵循 I1 的方向，所以是 I1 减 I2。OK， 好。然后呢，我们继续往下走，那碰到 R4， 那 R4 它也是电阻，所以它是耗能，那就是我们先碰到它的正极，所以是加号，然后乘上 I1 减 I3， 因为 I3 跟 I1 反方向，然后等于0，所以我们就得到我们的第一个式子。那同理呢，我们去看这个 loop 2， 就是右上方的这个 loop 或是 mesh， 那也是看 loop 3，那我们就是有列出这3个方程式，然后呢，我们 我们 focus 我们就令这个 loop 2的方程式为式1，令 loop 3的方程式为式2。那我们稍微做一点变化，我们把这个我们看式1好了。我们式1呢，我们就是把 i2 减我们 i2 减 i1 呢保留，然后把这个 i2 调到右边去，就是它乘负 r1 i2，就是变成负 r1 i2，然后我们同除以这个等式两边呢，同除以 i2，所以除以 i2，而且同除以 r2，那你就会变成是这样，就是对，然后第二式呢也可以变成下面这个式子。那如果 i2 等于 i3 的时候 ，i2 等于 i3 呢，它其实就我刚刚说的，就是我们可以用 a 来取代 i2 跟 i3，那你就发现呢，这两边都是 a 减 i1 除以 a， 所以意思是代表这两个式子的等式的左边呢，它们值都相同。那既然等式左边的值相同，代表它们等式右边的值也会相同，所以就是等式右边的值也会相同。最后呢，我们也可以得到 r3 等于 r1 乘 r4 除以 r2。OK， 那 r3 是未知的电阻，那 r1、r4 跟 r2 是已知的电阻。那我们就是可以，我们去调整 r4。那如果说我们这个中间可能 A、B 中间放一个电流计，当它们之间的电流为0的时候，那我们就是可以由 r1、r4 跟 r2 去计算 r3 的值。Okay, so this Wheatstone bridge, people use Wheatstone bridge all the time to measure the unknown resistance. So compared to this configuration, so if we want to measure the resistance of R3, this is Vs, this is Is, Vs and I, not Is. So if this configuration, the resistance of R3 equals Vs divided by I. Okay, however, if Vs is a battery, and we know that if Vs is a battery, maybe it's 10 volt, 5 volt. How about 5 volts? And then, but when we use a battery for a long time, it starts reducing its voltage. So after we use this battery for a long time, it may be the voltage of this battery maybe drops to 3 volts. And once it drops to 3 volts, and also it also reduces the current, which means R3, we may calculate a different R3. Okay, so the value of R3 will be affected by the voltage source. However, if we use Wheatstone bridge, you can see that this formula, it doesn't have Vs, which means this formula is unrelated to the voltage source. And it is more accurate. Okay, so this is the advantage of the Wheatstone bridge. It's unrelated to the voltage source and it is more accurate. Okay, and All right. And then the next example, we need to look at supernode. Okay, so when the current cannot be written in terms of single node voltage, we can define a supernode that includes several nodes. And also a KVL equation must also be written for the supernode closed surface. Okay, let's look at this example. So in this example, we need to find V1 and V2, and then we use nodal voltage analysis. So let me write it down. So by nodal voltage analysis. So for nodal voltage analysis, you need to define a reference node, which is here. It will tell you is connected to the ground. So this is V equals 0, right? And then since to the left branch, it goes through a 3 volts voltage source, which means this is 3 volts. And we define the voltage at node 1 is V1, the voltage at node 2 is V2, and here is also 0, right? Because these points, they are all connected together. So this is all 0. This is V0. And okay, how about we don't use supernode and then we apply KVL and let's see what happened. So we use KCL, not KVL. We use KCL because nodal voltage analysis, we need to use KCL. And KCL tells us the summation of the current flowing into a node is 0. So we look at node 1. So node 1, we have this, right? Because we need to define the current flowing into node 1. So its direction is like this. Since its directions from left to right, we have 3 minus V1 divided by 3K, right? This is the current flowing from this 3K ohm resistor. And then we need to define the voltage here, the voltage on the middle from bottom to top. So since it is from bottom to top, we have plus 0 minus V1, this is 0. 0 minus V1 divided by 5K, right? And then we need to define the current flowing from the right to the left. But so do you know how to define a current of flowing from the voltage source? No, we don't. So here, we don't know. So it becomes a problem. Let me put a question mark. We don't know. It becomes a problem. So because we don't know the current flowing out from the voltage source. So if there's a voltage source, and then we need to avoid the current flowing out from this voltage source. So the way to avoid to define this current, we define this whole thing as a supernode, which means we look at the whole thing, this V1, V2, and then this voltage source. We just look at it as a node, So this is supernode, and then we can start writing the equation. So we rewrite the KCL. So we rewrite KCL. So we look at this supernode, KCL at supernode. KCL as supernode. So we have this, again, the same thing. So let me erase this. We need to redo it. So let me start from the current flowing from left to right. So we have 3 minus V1 divided by 3K. And we also have the current flowing from bottom to top by the 5K resistance. So we have plus 0 minus V1 divided by 5K. And then we also, since we see this whole thing as a node, so we also have the current flowing through 3K. So we have plus 0 minus V2 divided by 3K. And we also have this, the current flowing from right to the left. So plus 0 minus V2 divided by 2K. So the summation of all these 4 currents flowing into this supernode is 0. Okay, so this is what the supernode means. But we need another equation, because right now there's one equation, right? But we have 2 variables, so we need one more equation. So for one more equation, we need to look at what inside the supernode. And you must know there's a 9 volts voltage source within the supernode, and these 2 points. So the relationship between V2 V1 is V2 plus 9 volts equals V1, because V1 would have a higher potential energy than V2, and its potential difference is 9 volts. So V1 is 9 volts higher than V2, which means V2 plus 9 equals V1. Okay, so this is the relationship between, let me write here. This is the relationship between V1 and V2. Okay, so right now we have 2 equations and 2 variables. So we can solve this V1 and V2. V1 is 6.22 volts. V2 equals minus 2.78 volts. And please calculate and double check. Okay, for this one, I want to talk in the class. So please review what we talked about today and do the homework. Okay, we will come back to this problem tomorrow.